Welcome to this deep dive. Today, we're jumping straight into something that might just change how you think about building antennas for ham radio.
Yeah, definitely.
We're exploring the work of John Portion, W6NBC. He uses some really, unconventional and inexpensive materials.
That's right. Forget expensive copper pipe or, massive aluminum tubing for a moment. We're talking aluminum foil tape, PVC pipe, stuff you can find at pretty much any hardware store.
So, our mission in this deep dive is to take the source material you've provided, articles, his research notes, video transcripts, all that, and really extract the most important knowledge and some surprising insights on his methods.
And we're focusing specifically on slot and magnetic loop antennas here.
Right.
We've used AI technology to help synthesize all this information, basically acting as a shortcut to understanding these, sometimes complex ideas pretty quickly.
Yeah, it's a great way to model how focused learning can really accelerate your path, maybe help you become a more skilled amateur radio operator.
Exactly.
And our hope really is that after exploring these ideas with us, you'll feel inspired. Maybe go back to the original sources, perhaps do some of your own experimenting.
Or even build one of these antennas yourself. See what happens.
See what you discover. Okay, so let's start with the man himself, John Portion, W6NBC. The sources paint him as a true expert, right? An award-winning antenna designer.
Yeah, absolutely. And what's really striking about his work, I think, is how he consistently challenges, well, decades of traditional antenna building wisdom.
He sounds like a real mythbuster. So what's his core philosophy? How does he get away with deviating so much from the norm?
His fundamental belief, it seems, is that you absolutely do not need expensive materials or, strict adherence to conventional size and shape rules to get high performance and efficiency from an antenna.
And cost is a huge driver for him, I gather.
Oh, absolutely central. He emphasizes that aluminum foil tape is, and this is his phrase, highly inexpensive and easy to get hold of.
Which is not what most hams think of first for a radiator.
Not at all.
But the cost difference he points out is just dramatic. Can you give us that example the sources mentioned?
Sure. They cite building a 4-foot square magnetic loop. If you use 1.5-inch PVC covered entirely in foil tape, it costs approximately $30 for materials.
$30. Okay, what would that same loop cost using traditional, say, 1.5-inch copper pipe?
The sources state it would cost $256. That's what it would cost for the same loop in copper.
Wow, $30 versus $256.
Yeah, so his method is squarely in the pennies cost solution category for, a potentially very effective antenna.
That is significant. And I understand his motivation often comes from some very practical problems, like antenna restrictions.
Exactly. He's often driven by these real-world constraints, like needing a good antenna where you're not allowed to put up big towers or wires. This kind of necessity pushes him to find creative solutions that, frankly, others might not even think are possible.
Okay, that makes a lot of sense. So if he's using materials like foil tape, which aren't, solid conductors like copper pipe, what's the basic principle that lets this work at radio frequencies?
It really all comes down to something called the skin effect. You might have heard of it.
Vaguely, yeah. Refresh my memory.
Okay, so at radio frequencies, the electrical current doesn't flow evenly through the whole conductor. It mostly flows right on the surface, the skin of the conductor.
Ah, okay.
The inside material is largely unused or essentially wasted when it comes to carrying RF current.
And the sources give us an idea of just how thin that skin actually is.
They do. For example, on the 80-meter band, the skin thickness is incredibly small, something like 1.7 thousandths of an inch in aluminum.
Wow.
And about 1.4 thousandths of an inch in copper. So really, really thin.
So if the current is only using that tiny surface layer anyway, what's Portion's big conclusion from that?
His surprising assertion, based on this, is that copper and aluminum are absolutely equal building materials for the efficiency of an antenna, if you apply them correctly.
Okay.
So this is why hollow tubes, or even plastic tubes like PVC just wrapped in foil tape, are just as effective as solid conductors for carrying RF. It's all about that conductive surface.
And this principle directly leads to another really crucial point about antenna efficiency, especially for certain designs like magnetic loops, right? The need for big conductors.
That's critical. Yeah. For maximum efficiency, especially at lower frequencies where, radiation resistance is naturally low, antennas really need conductors with large diameters, or maybe more accurately, large surface areas.
Why is that large surface area so important for efficiency? What's the mechanism?
Well, think about the antenna's resistance. It has two parts: radiation resistance and conductor resistance. Radiation resistance is good, that's power turned into radio waves.
Right.
Conductor resistance is bad, that's power lost as heat. Small conductors have relatively high conductor resistance, which leads to poor efficiency. Most of your power just heats the wire.
Ah, okay. So a big conductor gives the RF current more surface area to flow on, which dramatically reduces that conductor resistance.
Exactly. And that improves the ratio. More power gets radiated, less gets wasted as heat.
Makes sense.
And for magnetic loops, Porchin gives a specific guideline in the sources. The ratio of the conductor diameter to the overall loop diameter needs to be no less than 24 to 1 for really good efficiency.
24 to 1, that's a pretty chunky conductor relative to the loop size.
It is. It emphasizes just how important that surface area is for mag loops.
Okay, that fundamental principle makes sense now. It's about the surface, using big conductors cheaply. So let's look at some of the specific, unconventional designs Portion explores, starting with these slot antennas. His approach here seems to really throw out the rulebook on size and shape.
It really does. He starts by describing the fundamental nature of a slot antenna as being fundamentally similar to a folded dipole or one loop of a cubical quad, basically a one wavelength conductor wrapped around an empty space.
But here's the bit I found really counterintuitive. The sources state the metal plane surrounding the slot is the actual antenna, not the empty space, the slot itself. Is that right?
That's the key insight, yeah. The high intensity currents flow right at the edge of that opening on the metal. The slot itself is just where the radiation happens because of those currents flowing on the edge.
Huh.
And this also leads to that interesting complementary polarization thing. A horizontal slot is vertically polarized, and a vertical slot is horizontally polarized.
Which, for people operating on HF, having a vertical antenna structure that gives you horizontal polarization, that can be a big advantage for noise, can't it?
Oh, yeah. You often get less man-made noise on HF verticals with horizontal polarization compared to vertical, which tends to pick up more local electrical interference.
And Portion seems to just ignore all the standard rules for building these. What are some of the myths he busts?
Well, first, that metal plane surrounding the slot. It does not need to be a specific large size, like the old textbooks might say, 3/4 wavelength by half wavelength or something.
Okay.
He shows it can be almost any size, even very narrow. That's how he gets to what he calls a skeleton slot.
So you don't need this giant sheet of metal. What about the width of the actual slot, the gap?
That also seems to have very few restrictions. It could be almost any width, giving you a lot of freedom in how you build it.
And maybe the most creative part, the slot and the plane around it do not have to be flat or in the same plane.
Right, they can be bent, staggered, or even rolled into a cylinder.
And this is where his designs get really wild. The sources show examples like a staggered slot built right onto a window pane.
Yeah, using the foil tape.
The Lincoln hat, which is literally a rolled cylindrical slot antenna, an RV antenna design that's definitely not flat.
Right.
And maybe the most striking one, the slot cube, an 11-inch cube antenna that somehow performs as well as a 6-foot copper J-pole.
It's pretty amazing. That slot cube example really drives home that conventional size and shape aren't the only things that matter.
He also talks about optimizing where the antenna actually radiates from, right?
Yes, understanding that not all parts of an antenna radiate equally is important. You know how currents that are equal and opposite and close together, like on open wire feed line, they basically cancel each other out and don't radiate much.
Yeah.
You can use that principle. For instance, if you mount a delta loop antenna with the point facing downwards, you can encourage the main radiation to come from the top horizontal part.
Clever. And some of these unconventional slot designs actually offer gain too, not just efficient, but directive.
They can, yes. The double delta inverted skeleton slot, for example, is mentioned as providing azimuth gain and directivity. It focuses the signal horizontally in certain directions, giving several dB of gain over a standard vertical dipole.
Okay, so how do you actually tune these things once you've built them with foil tape?
Well, the primary tuning method is pretty simple, just physically shortening or lengthening the antenna a tiny bit, usually by literally moving a piece of aluminum tape to adjust the overall electrical length.
Sounds straightforward enough. But for HX slot antennas, there's a really critical rule about antenna tuners that Portune emphasizes very strongly in the source material.
Oh, this is absolutely vital. You cannot miss this. For HF slot antennas, it is critical to use an antenna tuner at the base of the antenna, not in the shack.
Not in the shack.
He really hammers this point home, even saying, do not do that.
And the reason is all about power loss on the feed line, the coax.
Precisely. If you have a high SWR, that's the impedance mismatch at the antenna, and you run your coax all the way back to the shack before tuning, you get significant power loss, eating you alive.
Turns into a dummy load, basically.
Pretty much. It just heats up the coax. And it can also potentially damage the rig's internal auto tuner if you try to make it handle that huge mismatch right at the radio.
So the tuner must go at the antenna itself, match the impedance right there before the signal even hits the coax.
Exactly. Get a good match to the antenna feed point. He suggests a manual L-match tuner placed right at the antenna base is a good, cost-effective alternative. Okay, so moving on from slots. Portion also applies these same core principles skin effect, big conductors, low-cost to magnetic loop antennas. And this ties right back to our earlier point about needing big conductors.
Right. Mag loops absolutely must have big conductors for good efficiency, especially on the lower bands like 40 or 80 meters.
Exactly. A larger conductor diameter leads to significantly better efficiency. Portion even suggests that using something really large, like a 6-inch diameter PVC tube covered in foil tape, would greatly enhance efficiency compared to, say, a loop made from 1-inch pipe.
And shape. Does he have an opinion on the optimal shape for these loops based on his work?
He does. He found, apparently through modeling and testing, that a square loop is the optimum shape for all magnetic loops.
Square, not round.
Square, not just electrically efficient, but he argues it's easier and less expensive to build, particularly when you're using large diameter PVC and foil tape. You avoid needing costly, bulky elbows for curves.
Ah, good point. Straight cuts, 90-degree joints.
Right. His advice is pretty blunt. Don't bother with round or rectangular, make them square.
Which brings us back again to the materials PVC and foil tape being his go-to.
Yes. For Porchin, PVC and foil is the optimized magnetic loop, not copper pipe. Again, it's that combination. The cost effectiveness is unbeatable, and the RF performance is essentially equivalent because of the skin effect.
Are there limits, though, to the size and frequency range you can cover with a single magnetic loop?
Oh, definitely. The highest usable frequency is limited by the loop's self-resonant frequency. It just won't tune higher than that point. For that 4-foot square loop example, the sources put this around 31.5 megahertz.
So good for 10 meters, but probably not 6 meters.
Generally not, yeah. And the minimum frequency is really limited by efficiency. As you try to tune lower and lower relative to the loop's physical size, the efficiency just plummets.
Makes sense.
He also challenges that old rule of thumb you sometimes hear that loops must be less in circumference than a tenth of a wavelength.
Oh, yeah.
He showed through modeling that the deep nulls, which are great for reducing noise, are still there, even when the loop is much larger, up to 7/10 of a wavelength in diameter.
Interesting. So you can build loops that are larger relative to the wavelength than traditionally thought, but efficiency is still going to be your main constraint on the low end.
Exactly. The practical reality, as the sources state, is there is no one loop that can cover all bands effectively. You probably need to build more than one if you want good performance across, say, 80 meters up through 10 meters.
What about power handling? Can these PVC and foil loops handle typical ham power levels? The sources mention voltage.
Yeah, he apparently calculated a maximum voltage of 2,000 volts for a typical PVC foil loop. He determined that the thickness of standard PVC pipe provides enough insulation for, 100 watts or maybe even a bit more, depending on the specifics.
Okay. And he also briefly touches on multi-turn loops. What's the advantage there?
Adding turns increases the radiation resistance. It actually goes up as the square of the number of turns.
Oh, okay.
So a 2-turn loop would have twice the efficiency of a 1-turn loop, all else being equal. He does recommend using odd numbers of turns, apparently to make impedance matching a bit simpler.
And for actually building and tuning these mag loops, any specific tips mentioned?
The sources include some practical advice on applying the foil tape smoothly, which sounds important. For tuning, he developed a clever sliding capacitor.
How does that work?
It uses an inner PVC pipe, also covered in foil, that slides inside a gap in the main loop conductor. This acts as a variable capacitor. It's described as a very low-cost alternative to those really expensive vacuum variable capacitors you often see.
Right, those can cost more than the rest of the antenna.
Easily. And this sliding capacitor allows tuning across a pretty broad range, like maybe above 10 meters to below 40 meters with a single loop structure. The matching network uses what he calls a universal optimized loop design with adjustable taps for the feed line.
So it seems across both slot and magnetic loop designs, Portune relies pretty heavily on testing and optimization tools. This isn't just guesswork.
Oh, absolutely not. He really emphasizes their importance. Tools like antenna modeling software are crucial. He specifically mentions EasyNet, which is apparently free now, and 4NEC2. These are highly recommended for modeling and designing antennas before building them.
So you can kind of design and test it all virtually on the computer before you even cut any pipe or stick any tape.
Exactly. These tools let you visually see current and phase displays. You can simulate changes to the design, like what happens if I make this conductor bigger or change the shape slightly, and really understand how different parameters affect performance.
That sounds invaluable.
Portune apparently uses them constantly to test his wild brainstorms for a new antenna before investing the time and materials to actually build a physical prototype. Saves a lot of dead ends, presumably.
And for people specifically interested in the efficiency numbers for mag loops, there was a tool mentioned for that too.
Yes, LoopCalc is recommended for calculating the expected efficiency of a magnetic loop based on its design parameters.
And then, once you actually build something, what's the key piece of test gear Portion uses to see how it performs in reality?
Antenna analyzers, often VNAs, vector network analyzers, these are essentials. They let you visually see the details about the antenna's resonant frequency, the SWR across different frequencies, impedance, stuff like that. Absolutely vital for fine-tuning the antenna. So, okay, let's try to wrap this up. To bring it all together, John Portion's work, as presented in these sources, it fundamentally demonstrates that you can achieve high-performance, compact, and really flexible antennas using incredibly cost-effective materials. We're talking aluminum foil tape and PVC pipe.
Yeah, and it's all grounded in a really solid understanding of core RF principles. Things like the skin effect, understanding radiation patterns, and especially the critical importance of conductor size for efficiency. Combine that with a willingness to just think creatively about construction.
And you get these designs that truly challenge the conventional wisdom. The idea that ham antennas have to be massive or prohibitively expensive or stuck in these rigid standard shapes we always see.
Which really leaves us with a fascinating question for you, the listener, to think about. If the skin effect means only the surface conductivity really matters for RF, and Porchin's work seems to prove that these unconventional shapes and super cheap materials can work effectively, what other inexpensive or maybe even recycled materials could potentially be used as antenna conductors?
Yeah, could we push the boundaries of accessible radio communication even further? What about, I don't know, metallized fabric, conductive paint? It really opens up a world of possibilities for experimentation, hasn't it?
Well, it really does.
We certainly hope this deep dive has been insightful, maybe given you some new ideas.
Definitely. Take these concepts, maybe check out the original source materials if you can find them, do some experimenting of your own, build something, see what we discover.